Assalamu alaikum guys. Our today's I am Dr. Sarfraz Ali with the subject Introduction to Riemannian Geometry. It's our 8th lecture. Our first topic is today theory of curves and surfaces. Guys, if there is some question for you, what is curve? Curve is a line, curve is a triangle, curve is a circle, curve is ellipse, curve is hyperbola. Actually, curve is a path of a point that moves in a space. A locus of a point is called curve. So, there are three figures. First of all, y minus 2x is equal to 1. This is a line. This line is also a curve with zero curvature. Y minus x is equal to 0. This equation is also a curve. It is a parabola. X square plus y square is equal to 1. This is a circle. This is also a curve. Now I define something here. If I define this line, there is no x, I mean there is only y is equal to 1, and it is a vertical line. These two stand for the slope of the line. I mean, what is the slope of the line? It is minus 2. Here is equal to slope is 2. And in this equation, this is actually given y is equal to x square. So in this equation, this curve, in first and second quadrant, if y is equal to minus x square, then this curve will be shifted here, like this. And if the major axis and minor axis are equal, then it is circle. If x square over some a square plus y square over some b square is equal to 1, then this will be the equation of ellipse. If a and b are not equal, then it is ellipse. Okay, it is well known from elementary geometry that a line in R2 or R3 can be described by means of parameterization, that is t to p plus q2, where q isn't equal to 0 and p are fixed vectors, and the parameter t runs over the real numbers. Likewise, a circle in R2, say with center 0, can be parameterized by t r cos t, r sin t, where t belongs to r. The common nature of this example is expressed in the following definition. Okay, before going to definition, here, if this mapping T, this component is for R, X, and this component for Y. So, if we put these parameters, mean these parameters R cos T, R sin T, in the previous equation, x square plus y square is equal to 1. There is a radius r. If this radius is 1, okay, if this radius r is equal to 1, then cos square plus sin square is equal to 1. So these terms, r cos t, r sin t, are the parametric equations for circle. And here and now, in as a definition, a parameterized continuous curve in Rn, n is equal to 2, 3 up to n, is a continuous map defined as some gamma such that I to Rn where I belong to real line. Uh, Unidirection is an open interval of endpoints minus infinite less than equal to a less than b less than equal to is there. Mean it's a real line. So this line, any mapping from this line with gamma on this one gives this equation. The form of any curve like this, if it is in as we consider here as any or n, how many dimensions here? If there are two dimensions x and y, then this curve becomes like this one. Example number one. The constant curve given by gamma of t is equal to t belongs to I for integer, interval where t belongs to Rn, if fixed and I some open interval is parameterized curve. Example 2, the map gamma of t is equal to a cos t, b sin t, where a be greater than 0 and are constants parameterize the ellipse c is equal to x y such that x square over a square plus y square over b square is equal to 1. If this a and b are equal, mean I call a and b are equal, mean this is a and this is a, then the same equation will become the equation of circle. Example 1.3, let gamma of t is equal to a cos hyperbola t, b sin hyperbola t, where a be greater than 0 t, and you know cos hyperbolic t is equal to e power t plus e minus t over 2, sin hyperbolic t is equal to e power t minus e minus t over 2. Using the equation cos hyperbolic square t minus sin hyperbolic square t is equal to 1. This is the this term is a hyperbolic identity. We see that gamma is a parameterization of hyperbola branch C such that this one. Or it can be if we put x is equal to a cos hyperbolic t here and b sin hyperbolic t is here, this equation becomes t square cos hyperbolic square t square over a square, then a square will be cancelled with a square and we remain with cos hyperbolic square t minus b square sin hyperbolic square t and b square will be cancelled, so we remain with x is over a square minus y square over b square is equal to 1. Here this term is given as x greater than 0. It means we want a hyperbola on right side of the axis. If x is a negative, if here is written y is positive, for example, or x is a negative, sorry, x is negative, we don't have, so we have y is negative, positive. If y is positive, then this line will become here, this. So guys, we are here. X square over a square minus y square of b square is equal to 1. If x greater than 0, then the uh, arc or a curve of a hyperbola on right side of the axis. And if y greater than 0, then this equation will become y square over b square or a square, what you like, minus x square over a square, then we are on this side. Okay, one thing more. Can you check these terms with uh, cos hyperbola, these terms, substituting this term and this term, putting here e power t plus e power minus t over 2 here and b into for sine hyperbolic t we put e power t minus e power minus t over 2 and then check this equation is satisfied. Okay, ji. Next example. The space curve gamma of t is equal to some lambda t or cos omega t or sin omega t, where r is positive and lambda and omega are not zero. Why not zero or constant is called a helix. There is one question. Why lambda and omega are not zero? Because if lambda is zero, so our first term becomes zero. So we remain with two coordinates. And if omega is equal to zero, then first term remain and this term become a r and sine zero is zero. That's why these lambda and omega are not zero. These must be some constant other than zero. Again, the space curve gamma of t is equal to lambda t or cos omega t or sin omega t, where r is a positive and lambda and omega not zero or constant, is called helix. It is the spiraling motion of a point which moves along the x-axis and velocity lambda, while at the same time rotating around this axis with radius r and angular velocity omega. So I hope you understand this definition of spiral helix, which is actually a spiraling motion of a point around an x. Here in this equation is given a x-axis. Uh, it is changing its position with angular velocity w and radius r, rotating about this axis. Okay. Now, the next is theory of surfaces. Definition: a parametrized continuous surface in R cube is a continuous map some sigma u to R cube, where u is subset of R square, is an open non-empty set. R square means a two-dimensional space. U is a subset of R square, and we're mapping from two-dimensional uh, two dimension to three dimension. So in two dimensions, we have any surface, any axis u and v. For this point P, this is called u, and we map through sigma on a three-dimensional space, which coordinates x, y, and z. Then this point map through sigma on here is sigma of p, and this is called sigma of u. This is actually R3 in coordinates. Here are three coordinates and here are two coordinates. It will often be convenient to consider the pair UV belong to U as a set of coordinates of the point sigma UV in the image S is equal to sigma U. However, sigma is not assumed to be injected. The same point in S may have several pairs of coordinates. Okay, we call a parameterized continuous surface smooth if the map sigma u to r cube is smooth. That is, if the components sigma I1 to 3 of this one sigma have three different images, sigma 1, sigma 2, sigma 3, have continuous partial derivatives with respect to u and v up to all others. We adopt the convention that a parameterized surface is smooth unless otherwise mentioned. Mean, here is a one more definition. Why it is smooth surface? If this surface has all continuous partial derivatives with respect to u and v up to all others, then it is called smooth surface. We adopt here in this case, for this definition, we are using parameterized surface is smooth, unless otherwise will be mentioned what it is. So first definition is plane. Let P, Q1, Q2 belong to RQ, R cube be fixed vectors and let sigma u v is equal to P plus U Q1 plus V Q2. For U V belong to U, which is a subset of R square, then sigma is a parameterized surface. If Q1, Q2 are linearly independent, the image this is a plane. Otherwise, it is a line or a point. Then it is a line if Q1, if one point, for example, Q2 is 0, then this term is equal to sigma is equal to P plus some U Q1, which will be the equation of line. And if both Q1 and Q2 are 0, if these Q1 and Q2 both are 0, then we remain only with P, that is a point. So for a plane, so this equation, a plane, if Q1 and Q2 are linearly independent, otherwise these will be 0. Otherwise, this is not an equation of the plane. Let next example for sphere. Okay, we are here for sphere. Let sigma u p is equal to cos u cos v cos 2 sin v sin u. These three parametric terms where u v belong to R square. This is the standard parameterization of the unit sphere. S square is equal to x, y, z belong to R cube case such that x square plus y square plus z square is equal to 1. The parameters u and v are called latitude and longitude, and together they are called spherical coordinates. Okay, here is one question. Taking care of all these parameter terms, cos u, cos v, cos u, sin u, and substitute in this equation. If these terms give answer 1, then it is a parametric equation, otherwise no. Okay, uh, so guys, you check it. Now the parameters u and v are called latitude and longitude, and together they are called spherical coordinates in a figure here. This is a sphere. If this u, and this v, this is called latitude and this longitude. Next example is cylinder. Let r is greater than 0 and put sigma uv is equal to r cos u cos v r sin v u, where uv belong to R square. The images S of sigma is the cylinder x, y, z such that x square plus y square is equal to R square. Uh, from here, substituting the value of x square plus y square, this gives R square. So this is the parametric equation. Here, this is this line x, this is y, and here is radius of this one. No, cone. Let lambda greater than 0 and sigma lambda u cos v lambda u sin v u. U v are from same domain. Then the image of sigma is the cone such that x square plus y square is equal to lambda square z square. Guys, to put these values here, x square plus y square, and solving them, in from here it will get square. This become lambda square u square cos square v. and this term plus lambda square u square sine square v and plus u square. Sorry, these two terms and uh, taking common lambda square u square, which become lambda square z square. So this is our for 4.